I'll explain asymptotic notations. They are big O notation, omega notation, and theta notation. And there are some other types of notations too, but I briefly introduce them. Look at this one. First, I'll explain the analogy between asymptotic notations and normal comparison signs. First one, f of n is big O of Gn, means function f of n is less than or equal to g of n in degree. For example, no examples. Then I'll show you an example. Assume that f of n is n and g of n is n squared. Then we can say f of n is big O of g of n. Because the highest degree of g of n is 2, but the highest degree of f of n is just 1. So we can write it in this form. Okay. Then the second one, f of n is omega of g of n. In this case, the degree of f of n is greater than or equal to the degree of g of n. In this case, g of n is big omega of f of n. Finally, f of n is theta of g of n. In this case, their degrees are the same. Let's say h of n is n squared plus n. Then g of n is theta of h of n. Since their degrees are the same. Let's think about this. Is it true or false? Is g of n big O of h of n? Is this true or false? It's true because there is a equality here, okay? And is this true? True, yes. If the degrees of two polynomials are the same, then we can use all of these notations. Theta, big O, and big omega. The essence of today's class is this. You should remember these things. And let me explain them one by one. The formal definition of big O notation is like this. Actually, big O of some function g of n is a set of functions satisfying this condition. I'll give you a minute. During that time, try to understand the definition of big O. It looks quite complicated. It isn't clear when you read this page for the first time. So before I explain this, I'll explain the upper bound. Okay? So assume that g of n is an upper bound of f of n. Then it means, okay, let's think about that. N is an integer and a positive integer, and g and f are non-negative functions. Then if g of n is an upper bound of another function f of n, then it means this. Okay? Simple. G of n is greater than or equal to f of n for all n values. This is the upper bound. Okay? In this case, it is a asymptotic upper bound. What does the asymptotic mean? There are two differences. One is this inequality don't need to be satisfied for all n values. We just restrict n where n is greater than or equal to for some n at some value and 0. Okay? Look at this graph. When n is below n0, smaller than n0, f of n can be larger than g of n. But when n is bigger than n0, g of n should be larger than f of n, larger than or equal to. And one more. We can multiply a positive integer c to g of n. In this case, g of n should be bigger than or equal to f of n. But in this case, we can multiply a constant c to g of n. So if we can find two constants, c and n0, then we can say f of n is big O of Gn. Then G of n is called an asymptotic upper bound of f of n. Okay, let's see an example. Three n plus 1 is big O of n squared. It's true because a simple explanation can be like this. The degree of and the highest degree of this term is 2. And the highest degree of this term is 1. So this, the degree of right-hand side is bigger than the degree of the left-hand side. So 3n plus 1 is big O of n squared. But this time, I'll explain that it is true using this notation. Okay? For 2 minutes, try to understand what this page says. 박종훈, sorry, this time let's go backward. Anna Katrina, what is the meaning of this line?
It says you should find two numbers, n and c, for which the equation.
Yes. Yes. This is the outline of the proof. What we should do is we have to find two constants, c and n0, satisfying this. Okay? So this is the proof outline. Okay? So proving using only the definition means finding two constants, two positive constants, c and n0, satisfying this. Okay. Okay? We are going to find c and n0 satisfying this inequality. Then let's find them. The first step we do is divide by n squared both sides. Then we get this inequality. 3n becomes 3 over n, and 1 becomes 1 over n squared. And this one becomes c. Okay, so if we find c and n0 satisfying this equation, they also satisfy this inequality. Okay? Then a simple observation will find n0 and c like this. Why? 이희준, can you explain?
First, the C can be proved by the second equation.
Second?
3 plus 1 divided by s squared.
So,
Yeah.
then what?
So C is equal or larger than 4.
Is it an alarm? Okay, 이문영. Is this function, the function on the left-hand side, is it increasing or decreasing? Increasing? Decreasing? As n gets larger, the value of the function becomes smaller. Okay? So it's decreasing. So when is it maximized? When is it maximized? We consider only integers in this case. So what is it? Four?
I don't understand.
So, 왕재민, when is this function maximized? We know that n is a positive integer. And it's decreasing. N equals 1, not 1. And when n is 1, it is maximized. And what's the value of it, the function? It's 4. Okay? So the maximum value of the left-hand side is 4. So if we set C as 4 or more, this inequality is satisfied. So one possibility is n0 is 1 and C is 4. Or any value for larger than 4 is fine. So since we can find a pair, it's done. We proved. Okay. And let's consider the omega. In this case, and this is very similar to the big O notation. Only one thing, except the only one thing. In this case, we find a constant C and n0 satisfying this. C times G of n should be smaller than or equal to f of n. All the other things are the same. In this case, G of n is called an asymptotic lower bound of f of n. Let's see another example. 3n squared minus 4n plus 1 is omega of n. A simple observation is this is a quadratic function and its highest degree is 2. And this is a linear function, So its highest degree is 1. So simply, this is a big omega of n. And the formal proof is here. And look at this page and try to understand the proof. The meaning of this line is we are going to find Cn and 0 satisfying this inequality because it is omega. Look at the direction of the comparison operator. This one should be greater than or equal to this one with the good choices, with a good choice of C and 0. Then try to find C and 0. The first thing to do here is divide by n, divide all terms by n. Then we get 3n minus 4 plus n over 1. Then look at this. 김태현, 김원종. Is this an increasing function or decreasing function? Right? Increasing function, but it is very hard to find. First, it decreases and increases. Or, look at this. This is the decreasing part, and this is the increasing part. But look at this. When n is 2 or more, then the left-hand side is 2 or more. Okay? This is anyway positive. Okay? And if n is 2 or more, then 3n minus 4 is always 2 or more. Okay? So, if we set n0 as 2 or more and c is 2, this inequality is satisfied. Finally, theta notation. This is both big O and omega notation. In this case, if f of n is theta of g of n, then for two constants, C1 and C2, C1 times g of n is below or equal to f of n, and C2 times g of n is above or equal to f of n. So in this case, we have to find three constants, C1, C2, and n0. And we say g of n is an asymptotically tight bound for f of n. Let's see. This is an example of theta notation. This is a quadratic function, and this is also a quadratic function. So their degrees are the same. So this one is theta of n squared. then we have to show that for some positive constants C1, C2, and N0, these two inequalities are satisfied. C1 times N squared is less than or equal to this, and C2 times N squared is greater than or equal to this. For all N greater than or equal to some constant N0. Okay? Then we first divide all terms by N squared. Then we get this simple form. This is not difficult. From this simple form, we can find C1 is smaller than or equal to 1/14, and C2 is at least a half, when N0 is 7. First, look at this inequality. Let's find C2 first. Look at this. So this function is bounded above by a half. Because n is positive and there is a negative sign here, this cannot be bigger than a half. So if we set C2 as a half, it's enough. A half or more, it's enough. And let's look at the other side. Is it increasing or decreasing? Increasing. Okay? Then, but in this case, C1 should be positive. When n is 1, it is negative. When n is 2, it's still negative. When n is 6, it's 0. When n is 7, it becomes positive for the first time. And its value is 1/14. So from then on, it's bigger than 1/14. So C1 is 1/14, C2 is 1/2, and N0 is 7. Then we can satisfy these two inequalities. Then it's done. It looks quite difficult, but if you practice several times, you will get used to it. In general, you can show that any quadratic function is theta of n squared. you can use the same technique to prove this. So this is a self-study topic. In general, for any polynomial whose degree is d, whose highest degree is d, then it's theta of n to the d. Okay, and some theorems. That's not difficult. If f of n is theta of g of n, then f of n is big O of g of n, and f of n is omega of g of n. If you read the definition carefully, it's quite straightforward. It's true by definition of big O and omega. Okay, I will skip this page. There are more definitions, but they are rarely used. These three definitions are important. Theta means the degrees are the same. Big O, then this degree is bigger. Omega, this degree is bigger. Bigger than or equal to. But there are small, little o and little omega notation. What are the differences between little notations and big notations? 김원종, you did. 김영민, what's the difference between little o and big O? And yes, there is an equal sign here. It means if f of n is n squared and g of n is n squared plus n, this is true. But in this case, there is no equal. So the degree of g of n should be strictly larger than the degree of f of n. Strictly larger. Is there any example? For example, okay. N squared plus n is big O of n squared. This is true. But n squared plus n isn't little o of n squared because 2 degrees are the same. But what if the degree is 3? Is this true? True? Yes, true. How about this? True? So this is true when the degree is strictly greater than this degree. And the little omega case is similar. In this case, the degree of g of n should be strictly smaller. And I'll skip details of little o and little omega. I will explain comparison of functions, transitivity, reflexivity, symmetry, and transpose symmetry of the asymptotic functions. Before I explain this, I'll explain these of their analogies. Do you know what transitivity is? Is there any? Let's go. Transitivity. Transitivity means this. The equality is transitive. That is, if A equals B and B equals C, then A equals C. This is transitivity. So equality is transitive because this is satisfied. And less than or equal to is also transitive. That means if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. Okay? And transitivity is satisfied for all these comparison operators. And you know that. Okay? And similarly, for all asymptotic notations, transitivity is satisfied. If f of n is theta of g of n, and g of n is theta of h of n, then f of n is theta of h of n. Because, as you know, theta is similar to equality. And this is also true for big O, big omega, or little o, little omega. Okay? Then let's move on to reflexivity. What is reflexivity? It means for an operator, you know that A equals A. Then this equality is called reflexive. So you can put the same operands on both sides. Then the operator is called reflexive. And we also know that this and this operators are reflexive. But is this reflexive? No. Is this reflexive? No, they aren't reflexive. So only 3 operators are reflexive. Similarly, only 3 asymptotic notations are reflexive. As I said, little omega and little o corresponds to these operators. So, because these operators aren't reflexive, those asymptotic notations aren't reflexive either. next two things, symmetry and transpose symmetry. Symmetry is like this. If A equals B, we know that B equals A. This is symmetry. Then, is this operator symmetric? If A is less than or equal to B, then B is less than or equal to A? No. So all the other operators aren't symmetric. So only equality is symmetric, and only theta notation is symmetric. Instead, the other operators have transpose symmetry nature. That is this. If A is smaller than or equal to B, we know that B is greater than or equal to A. So we can swap the operands with replacing the operand. So this is called a transpose symmetry. So there is a transpose symmetry between less than or equal to and greater than or equal to. And there is another symmetry, a transpose symmetry between less than and greater than. Similarly, there is a transpose symmetry between big O and big omega. If f of n is big O of g of n, then g of n is big omega of f of n. And another one, if f of n is little o of g of n, then g of n is little omega of f of n. Yeah, this is the last page. So I'll explain trichotomies. Do you know trichotomy? So is there anyone religious? Catholic? Christian? Trichotomy. Don't know? Check about it. So the trichotomy in religion is different from the trichotomy here. It is for any two real numbers, A and B, exactly one of the following must hold. Either A is smaller than B, A equals to B, or A is greater than B. That means we can compare A and B for any real numbers A and B. So two real numbers are always comparable. That is the definition of trichotomy. But it isn't true for the asymptotic comparisons. We think that means if we are given two functions f of n and g of n, if they work comparable, then they are either, f of n is either g of n, big O, one of them should be satisfied if the trichotomy is true on asymptotic comparisons, but it isn't true. Sometimes, actually, theta of Gn is not important because they include equals in big O and big omega. If they were comparable, one of them should be true. But there is a case both of them aren't true at the same time. So the trichotomy isn't applied to asymptotical comparisons. This is an example, n and n to the 1 plus sine n. Let's draw a graph of them. This is n, a linear function. And then how about n to the 1 plus sine n? It's n times n, okay, this is, look at this, n sine n is between n0 and n squared, right? Because it oscillates between -1 and 1. This 1 plus sine n oscillates between 0 and 2. Okay, so this is n squared, and this is n0. Okay, n0 is 1. So it's something like this. So you can't find, this is a constant function, and this is a linear function, and this is a quadratic function. So you know that this one is big O of this, and this, this one is big O of this, and this is big O of this. But this function oscillates between a constant function and a quadratic function. So this is sometimes an upper bound of this and sometimes a lower bound of this. So we cannot say this is an upper bound or a lower bound of this function. Okay? Any questions? Okay, I have an announcement. Our programming server is perfectly installed. So you can log on to our programming server and you can submit your programming assignments. you can read and your programming assignment from our programming server. Then submit your assignment and run your program on the server. Then it will return you that your program is right or not. So during Chuseok holiday, you can do your programming assignment. Okay, then let's wrap up this class now and see you the week after. Okay, bye.